Hello. In today's computer interfacing and microprocessors lesson, we are going to be discussing about system on a chip. And then also we will briefly go through what the ARM architecture is. So when we talk about a system on a chip, what we mean by that is this is where we have a computer system, essentially the main hardware components of a computer system is made available on a single silicon substrate. So basically on a single chip. And essentially, this would also include the components that are going to house the software aspect of it. So both the hardware and software are going to be inside the same chip. Hence the name system on a chip. So what this chip will have is all the hardware packages necessary, all the electronic components that is necessary for essentially a full-blown computer. It doesn't mean that it is going to have screen and all the other input output devices and all that, but essentially most of the controllers and all those things will be included inside the chipset. So then whatever the necessary software components are also going to be embedded into the same hardware chipset. One of the main reasons why we would use a system on a chip type devices are mainly they can yield low power or they can run on a low power consumption, and also in many situations they can be low cost devices as well. And also they can be more reliable than multi-component devices because they can be manufactured as a single device. So the points of failure are much less compared to multi-component systems. So building multi-component system. One of the things to remember that why system on a chip type devices have gained traction in the recent past is that the technology has advanced significantly. Particularly, there have been a lot of advancements in semiconductor manufacturing. The cost of such devices have gone down. So the number of transistors that we can fit in a single chip die, for example, has increased a lot, and also cost per transistor has gone down significantly. So the combination of these two factors has resulted in us being able to build such system on a chip type devices. So when we think about a general system on a chip idea, here what we may have is essentially we may have a processor, then we may even have some other co-processors, other sort of processing elements. We may have certain media processors like graphics processors and so on. We could have memory components and various other circuitry and other system components. And all of these things interconnected using some common bus or a number of buses. So essentially, whatever the computer architecture that you may see as a von Neumann computer architecture, for example, most of those components will be already being built inside a single chip here. So this single chip is going to be able to function as most of the components that you would need to set up a computer. Then you may still need a few other components, as I mentioned, things like certain input output devices, things like that may have to be interfaced with this. But other than that, most of the essential computer components will be included in this chip itself. If we look at even more sort of detailed structure of an example, here what we may have is, say, a processor, certain power supply components may be there, a memory controller may be there, and that may support a number of memory technologies and even sometimes may support external memories. There can be a number of communication protocols being supported, communication interfaces, various USBs and all these different communication interfaces, and all of these being interfaced through certain peripheral bridges to the processor. So this is what we would have in a system on a chip. So not just the main components, that even sort of specific components is, for example, these are sort of common communication protocols that you may find in embedded system applications. So there you may have such components as well. So when comparing a system on a chip or with a single processor on a chip, so that is essentially just a processor on a chip, a microprocessor on a chip, we can see a number of differences. For example, on a system on a chip, it would have a number of different processes included. So there will be the main core processor, there would be other media processors, so there will be a number of these elements being part of such a system on a chip. Whereas processors may have a number of processor cores, but that's about it in most situations. Whereas processors sometimes may have multiple levels of cache memories and things like that, because that is the nature of the processing requirements in such situations, whereas that may not be the case in certain system on a chip implementation. It's not that it can't happen, but that may not be the general expectation there. Whereas when we think about memory, again, most of the time on a system of a chip, it would be an embedded memory, whereas on a processor environment, or standalone processor environment, memory is normally a external standalone device. Most of the time, system on a chip chips are normally special purpose devices, so they will be manufactured for certain application domains. Some may be built for audio related, some may for networking related, some may for graphics processing related. So, but there will be some special purpose. The functionality may be geared towards a special application, whereas most general processors are aimed for general purpose use. Then SoCs will also support a lot of interconnect bandwidth, so they will support various interconnect capabilities and things like that. Whereas processors, there's only sort of through cache memory, there's like through memory-based communication is the main one that would be available there. When we think about power and cost, things like that, system on a chip are generally low cost and low power devices compared to processors that may require more power and could be more expensive. And given that most of the functional components are already included within the system on a chip, they can largely function as standalone devices with the addition of certain auxiliary components like power supplies, input-output devices, and things like that. But whereas processors will rely on a lot of other processors, other chips, for example, to give other functionalities to make up a proper computer or a full computer. So with this, we can see one of the main sort of differentiations that we can draw from here is the nature of special purpose processors with system on a chip being low cost or low power devices. That is one of the important factors that we will see. That they can function as standalone devices is an important factor there. So these are some of the main sort of advantages that we would see in using system on a chip applications. particularly in certain application domains. One of the common places, one of the most common situations where system on a chips are used are what we can categorize as embedded systems. So again, when we talk about embedded systems, they are sort of a large variety of things. And one of the things to remember is of all the processes that are generally manufactured, a large number of them end up in such embedded systems. And many of those would be in the form of system on a chip as well. So these could be industrial robots, mobile phones, routers and other networking devices, media players, cameras. So a lot of these devices may use system on a chip based implementations there. Some of the main reasons why we would go with system on a chip approach when we are building embedded systems is that many embedded systems would have limitations in terms of power consumption. They may be mobile devices, battery powered devices, and SoCs are power efficient in many cases. We need highly reliable devices. Again, many of these embedded systems may run in extreme environments, high temperature environments, things like devices, control system devices that are running in manufacturing plants, for example. Then we may have certain real-time operation requirements. Again, many embedded systems may have certain real-time requirements where predictable performance is needed. So we may use certain special purpose-built system on a chip devices there rather than using general purpose processors. Some of these systems can be highly complex. For example, if we take a modern automobile, for example, they can have more than 50 electronic control units and things like that. So again, having specialist processors and capabilities like that built on special purpose processors may be advantageous. And given most embedded system applications are tightly coupled software and hardware implementations, it would be advantageous when we use these specialist system on a chip processors to build these systems. And in a way, they can also lead to low cost development cycles and things like that. So for a number of these reasons, to meet a number of these challenges that we may face with embedded systems, many of these can be addressed through using system on a chip based approaches. So that's one of the reasons why they have a higher uptake in this sector. Then another factor that we may see is the gap between hardware advancements in hardware design technology and software technology and the overall system design approaches, and using a combined approach like system on a chips software hardware combined approach can be a solution where we go in a sort of high level of abstractions and things like that to solve this gap that we may encounter there. So when we talk about these multiple levels of abstraction, one of the things that we can start with is sort of the low level circuitry. So that is the low level network of transistors. Then the next level of abstraction is the logic gates, the logic level abstraction. Then the next level is the processor level abstraction. And system on a chips are the next level of abstraction where we have in addition to the processors, we also include memories, buses, and other processing logic included at that level of abstraction. So again, we go at the next level of abstraction to gain certain advantages in terms of design and things like that. So when we think about designing a system on a chip, what we would try to do here is go through a design flow. This sort of illustrates sort of a basic design flow that we can take when we go about doing an SoC design. So we may start with a system specification, so that is identifying what we want to do, and then from there we would divide those things into what are the hardware components and what are the software components. So then we can go into two separate models of hardware and software development life cycles, and each of those things, so we will go and synthesize a hardware model and implement a hardware model, and then we can do verification. And similarly, with when hardware model is being verified, we will use the software that is implemented on the hardware for the verification process. So the software will be compiled and that binary image will be used. So that is where we would do the verification process. So then when things are acceptable, then we will do the system integration and implementation, sort of the final implementation there. So this is sort of the overall higher level design flow that we would take when we go about designing a system on a chip. When we talk about system synthesis, specifically from a hardware point of view, when we are talking about these devices, what we try to do here is mapping processes into logics. So identifying what is going to be the hardware aspect, what is going to be the software aspect, identifying the communication things, communication requirements, identifying the buses, what are the necessary communication buses and things like that. And then we go about identifying all the requirements, all the scheduling requirements, all the components, identifying the various components and things like that. And at a much higher level, what we would try to achieve is starting from sort of component selections, then going through the various cycles of identifying each of the components and building at a sort of a multiple levels, and then we can come to the sort of the final structure that we want to build. So one of the main things to sort of identify when we talk about SoC based approach is that we are going to take up a hardware software co-design approach. So that is the design approach is both considering the hardware components and the software components together to achieve the final outcome. Say, for example, if we take a simple example that many of you would be familiar with is a smartphone. So in the case of a smartphone, the underlying software architecture and whatever the new hardware components that will be introduced on a new version of a smartphone, they will have to be considered hand in hand. So if they are introducing a new camera module, if they're introducing a new communication module, say for example 5G, they are supporting 5G in the new smartphone module. So then there should be certain hardware components to do that, radio controllers and things like that. Then at the same time there should be certain software components. So these things too needs to be designed together. So there should be some synergy between hardware and software design approaches, and those things sort of inform each other and take on from each other. So that is one of the main sort of approaches that we would see when we are thinking about SoC designs. Then finally, when we think about SoC designs at an even sort of a higher level, we would have things like sort of when we are designing these platforms, we would reuse components. So that is like, say, if we would talk about these various components. So when we talk about an SoC, we said a basic SoC is going to have a number of components like processor, memory, and IO modules, and so various components are going to be there. So then what is going to happen is we could reuse a number of these components. So we may use already designed IO modules, already designed memory modules, already designed processor modules, and we can bring those things together, pre-existing designs, and then we can package them together to create a particular SoC. So we may add components as necessary. For example, we may add more communication components if that is the nature of the SoC that we are building. We may add, say, graphics components if that is the nature of SoC that we are building. So likewise, we may implement or we may add on more components from our set of pre-existing components, and then all of those things can be put together and synthesized. So what are the sort of advantages that we get from this type of an approach is that we can very quickly develop a new iteration of a device, so new revision of a device. We can develop these things at a lower cost because we are reusing these components or reusing these component designs and things like that. So we don't have to go into a full-on design. We are reusing some of these approaches. So that is one of the sort of fundamental ideas that we would have in terms of designing these SoCs, recapturing them as these platforms and predefined components, and then the aspect of reusing in that level. So when we talk about SoCs these days, one of the most common aspect of many SoCs that we may come across, particularly in many sort of mobile application domains, in many communication application domains, is the processor component. As we said, these are predefined components that are going to be synthesized together, and one of the most common components from a processor point of view that we would come across is the ARM architecture. So you may come across a mobile phone, a smartphone SoC that may have an ARM processor. You may come across an SoC for a networking device, a router, for example, that may have an ARM processor. So the idea behind these ARM processors and ARM architectures is so fairly prevalent in the SoC world. So we will briefly look at what the ARM architecture is and what are ARM processors and things like that. One of the main reasons why we look at ARM, particularly in this case, is that it has a very high market share in terms of being used in sort of these type of applications. It is a common architecture that can be implemented by different vendors, for example. So it is not a single, they are not a processor manufacturer. They are like a processor design that will be licensed and manufactured by different vendors. Say, for example, Apple uses ARM processors, Samsung uses ARM processors, many other vendors use ARM processors as well. And they are built for the purpose of mobile in first in mind sort of thing. So they have low power consumption, low cost, providing high performance. So these are some of the advantages that we would see, and they are found in sort of many different applications, like in automotive applications, industrial applications, communications applications, even certain sort of specialized applications like security, sort of smart cards and that type of applications as well. So if we just look at briefly talk about the history of ARM, for example, it started in sort of sometime in the 80s, but their first set of processors came about in sort of particularly the ARM processors came about in the 90s. And since then, they have become sort of the leader in embedded CPUs or CPU cores that are used in SoCs, embedded applications. They have become the foremost option by many vendors, many manufacturers. So one of the other interesting factors about ARM is that ARM architecture is the one that is the organization ARM, they are responsible for coming up with these new architectures, new revisions of architectures, identifying the instruction sets, programmers models, exception models, memory maps, and things like that. So they define the architecture, and then various vendors can license that architecture and go on and implement and manufacture those processes. So that is one of the main differences that we would see between ARM architecture and ARM processor. And particularly processors are again not manufactured by ARM itself. Again, they are the designers. They are normally manufactured by third-party vendors. One of the main factors that results in ARM being more sort of power efficient, more low cost, more sort of compact, and all these things is that it is a RISC processor, and it takes upon all the sort of features of RISC processors, things that we have discussed previously in this module. So they have a large sort of uniform register file, so they can process that will assist in going on about processing in a lot of instructions. They have which can also result in data processing operations directly operating on registers. They have simple addressing modes. Then they have also uniform and fixed length instruction fields. So the instruction decoding and things are much better. So again, many of the advantages that we have discussed in RISC computers, all of those are available with ARM architecture as well. But in addition to that, ARM instructions, there are certain additional instructions that can provide certain advantages in terms of maximizing the ALU, or rather the use of ALU and shifters, and certain auto incrementing addressing modes, certain multiple load and store instructions, and conditional execution. So these are some of the things that sort of enhance the performance capabilities, enhance the speed of the devices, but still, so that is achieving sort of higher performance, but still being low power consumption and low silicon area devices. So that is one of the main sort of advantages that we get from these ARM architecture devices. And then we go about ARM architectures and ARM processor families, particular processor designs. There are, again, different processor designs aimed at different application domains. So we have mobile specific processor designs. We have high-end application specific designs, things that may be used in smartphones and netbooks and even laptops these days. Then we have certain real-time specific processor designs that are meant for real-time applications. And then we have secure core processor designs that are there for building security features in smart cards and things like that. Encryption and all these features may be present predominantly in those models. So when we think about the processors, again, just basically touching through some of the aspects of ARM processors, they go through a number of additional processor operating modes, things like user mode, so that is the unprivileged mode where most tasks run. But other than that, they have a higher priority mode, lower priority mode when interrupts are raised, depending on the nature of the interrupts. Then there is a supervisor mode, there's a system privilege mode, and things like that. So again, these are some specific aspects of ARM processors. One of the main features that we would identify with ARM processors is the register set that is available in ARM processors. There are some special purpose registers and some general purpose registers, and some can act as both depending on when they are being used. So again, that is something that we would consider based on what we are trying to do. Then when talking about the particular instruction set architecture of ARM devices, there's the ARM instruction set architecture. Uh, we are not going to go into the details of different versions of instruction set architecture, but it is suffice to say with each iteration there are new additions, new improvements that have been done with each of the iterations of the ARM instruction architecture. And there are improvements in the address space. For example, they started with say the lower to extended to 32-bit operations, and then they started adding various additional sort of instructions, thumb instructions and things like that that came about later on. And in much later versions, there are much more sort of higher end features that have resulted in ARM processors being used in many sort of high-end applications, things like multi-processing, multimedia support, memory management capabilities, again, things like that which are necessary when we are building higher end applications like smartphones and laptops and things like that. Then one of the other sort of factors that we may see particular for ARM processors, ARM architecture, is what is known as the thumb instruction set that came about with the instruction set version 4. So what we have here we have some instructions that are half size, so some are 16-bit whereas others are 32. Then with these half size instructions we can have higher density of code, so again low code footprint and all, which can be advantages when we are particularly considering embedded applications and things like that. Then from a system on a chip point of view, ARM also implements what is called advanced microcontroller bus architecture, or AMBA, which is a set of protocols that are there to support on-chip interconnection. So all the various components that are on a chip itself and how they may interconnect with each other. So that is the main aspect of advanced microcontroller bus architecture. So again, this is a specific aspect of ARM and particularly supporting such devices. And finally, one of the interesting factors that we may come across, we can see, is that even though ARM started as, and like it is still very much has a big foothold in embedded applications, but slowly it is taking place at sort of replacing many of the general purpose computing applications. It started with its use in smartphones, but now there is a quite lot of uptake in ARM processors in laptop computing, in general purpose computing, in servers. There's expected many vendors are bringing in ARM-based laptops these days. There are many sort of cloud-based providers that are providing ARM-based servers available through their cloud provisions. So because ARM was from the beginning, it was designed for low power applications, the RISC design. It has always the advantages of being low power, low heat, low cost. All these things are advantages when compared to x86 or general the architecture that is normally prevalent in normal compute applications. So that is one of the reasons why we are seeing ARM processors beyond SoCs, beyond embedded applications these days, and that trend is set to grow anyway. But in the domain of SoCs also, they still have their significant foothold, and that is also expected to remain as it is. So there are a number of resources that you can refer and get a bit of understanding about ARM processors, ARM architectures. which would be interesting and useful for you all. And with that, that's all for today's lesson. If you have any questions and if you have any concerns regarding this module, any of the topics that we have discussed so far, feel free to share those, and we will try to have a discussion on Google Classroom, and if needed, we may have a online discussion as well. So that's all for today. Thank you for joining. See you next time. Bye.